Welcome to this lesson on the nanoparticle melting point depression reversal paradox. This is a fascinating phenomenon in nanoscience, where some nanoparticles melt at lower temperatures than their bulk counterparts, while others surprisingly melt at higher temperatures. Let's start with the classical understanding. For most materials, as we reduce their size to the nanoscale, the melting point decreases. This is called melting point depression. For example, bulk gold melts at 1064 degrees Celsius. But gold nanoparticles can melt at temperatures as low as 300 degrees Celsius when they're only a few nanometers in diameter. Why does this happen? The key lies in understanding surface energy and thermodynamic stability. In a nanoparticle, a large fraction of atoms are at the surface compared to bulk materials. These surface atoms have different bonding environments. Surface atoms, shown in red, have fewer neighbors than interior atoms, shown in blue. This means they have unsaturated bonds and higher energy. Surface atoms are less coordinated. They're missing neighbors on one side, which makes them less stable energetically. The melting point depression is quantitatively described by the Gibbs-Thompson equation. This is one of the most important equations in nanothermodynamics. The melting temperature as a function of radius r equals the bulk melting temperature times 1 minus alpha divided by r. Here, Tm of r is the nanoparticle melting point, Tm bulk is the bulk melting point, r is the particle radius, and alpha is a material-dependent constant. The constant alpha equals 4 gamma SL times Vm divided by delta HF, where gamma SL is the solid-liquid interfacial energy, Vm is the molar volume, and delta HF is the latent heat of fusion. The key insight is that the melting point decreases inversely with radius. As particles get smaller, the melting point drops more dramatically. Let's work through a concrete example with gold nanoparticles to see how significant this effect is. The bulk melting temperature of gold is 1337 Kelvin, which is 1064 degrees Celsius. The solid-liquid interfacial energy for gold is approximately 0.132 joules per square meter. The molar volume of gold is 1.02 times 10 to the negative 5 cubic meters per mole. The latent heat of fusion is 12.55 kilojoules per mole. When we calculate alpha, we get 4.3 times 10 to the negative 10 meters, or about 0.43 nanometers. Now let's calculate the melting point for a 2 nanometer radius gold nanoparticle. Tm of 2 nanometers equals 1337 times 1 minus 0.43 divided by 2, which equals 1337 times 0.785, giving us 1050 Kelvin. That's about 777 degrees Celsius. The melting point dropped by nearly 300 Kelvin just by reducing the particle size. This is a huge effect. Now here's where things get really interesting. Some nanoparticles actually show the opposite behavior. Their melting point increases compared to bulk. This is the paradox. You might ask, how is this even possible? If surface energy always destabilizes particles, shouldn't they always melt at lower temperatures? The answer lies in 3 key factors: surface ligands, internal strain, and particle shape. These can completely reverse the expected behavior. The first factor is surface ligands. When nanoparticles are capped with organic molecules or other ligands, these can dramatically stabilize the surface. Here we have a metal nanoparticle core in gold, surrounded by a shell of ligand molecules shown in green. These ligands bind to surface atoms and satisfy their dangling bonds. Strong ligand binding can reduce the surface energy so much that the effective interfacial energy becomes negative in the Gibbs-Thompson equation. The effective surface energy equals the bare solid-liquid interfacial energy minus the ligand contribution. If the ligand binding is strong enough, gamma effective can become negative. When gamma effective is negative, the correction term in the Gibbs-Thompson equation becomes positive, leading to melting point elevation. For example, gold nanoparticles capped with long-chain alkanethiols can show melting points 50 to 100 Kelvin higher than bare particles of the same size. The second factor is internal strain. Nanoparticles often have significant lattice strain due to surface stress and faceting. In bulk crystals, the lattice is regular and unstrained, but in nanoparticles, surface stress creates compressive or tensile strain throughout the particle. Surface atoms are pulled inward by unbalanced forces. This creates compressive strain in the particle interior, reducing the lattice parameter. The change in melting point due to strain is given by delta Tm equals negative Tm bulk times delta 5 over V delta HF times sigma, where sigma is the applied stress and delta 5 over V is the volume change on melting. For most materials, compressive strain increases the melting point because it makes the solid phase more stable relative to the liquid. Nanoparticles can have lattice strains of 1 to 5%, which can shift melting points by tens of Kelvin. The third factor is particle shape. The melting behavior depends strongly on whether particles are spherical, cubic, rod-shaped, or have other morphologies. Different shapes have different surface-to-volume ratios and expose different crystallographic facets. Each facet has its own surface energy. Faceted particles exposing low-energy crystal planes can be thermodynamically more stable than spherical particles, leading to higher melting points. The total surface energy equals the sum over all facets of area AI times surface energy gamma I. Minimizing this determines the equilibrium shape. Gold nanocubes exposing 100 facets can have melting points 20 to 30 Kelvin higher than spherical particles of the same volume. Now let's put it all together. Whether a nanoparticle melts at higher or lower temperature than bulk depends on the balance of all these effects. The size effect always decreases melting point. Ligands and strain typically increase it. Shape effects can go either way. The net result depends on which effects dominate. The total change in melting point is the sum of contributions from size, ligands, strain, and shape effects. Let me give you an analogy to understand this paradox. Imagine a ball sitting on a hill. The ball represents the nanoparticle. The height of the hill represents the energy barrier to melting. For a bare nanoparticle, the barrier is lower due to surface energy. But when you add ligands, shown as blue spikes, the barrier becomes higher. The ligands stabilize the particle, making it harder to melt. This is like building up the hill. The paradox is resolved by recognizing that there are multiple energy contributions that can either stabilize or destabilize the solid phase. What do experiments actually show? Different nanoparticle systems exhibit wildly different behaviors. Bare gold nanoparticles show classic melting point depression. A 2 nanometer particle melts around 600 to 700 degrees Celsius, much below the bulk value of 1064. But thioprotected gold clusters of similar size can have melting points at or even above the bulk value due to strong ligand stabilization. Tin nanoparticles embedded in aluminum matrices show melting point elevation due to compressive strain from the matrix. Lead nanoparticles in aluminum show depression because the lattice mismatch creates tensile strain. Bismuth nanowires can show elevation due to quantum confinement effects that stabilize the crystalline phase. Let me write down the most complete equation that captures all these effects together. Tm of R equals Tm bulk times a complex correction factor. The first term is size and ligand effects, with gamma L being the ligand contribution. The second term is the strain contribution, with sigma being the stress. The third term captures faceting effects with delta G facet. Each term in this equation can be positive or negative depending on the specific system. This is what creates the paradox. The behavior is highly system dependent. Why does this matter? This phenomenon has profound implications for nanotechnology applications. Nanosoldering exploits melting point depression. Silver nanoparticles that melt at 150 degrees Celsius can join components at low temperatures, then solidify into bulk-like material. Understanding when particles melt at higher or lower temperatures is crucial for designing thermally stable nanoelectronic devices. Catalytic nanoparticles must remain solid at reaction temperatures. Ligand engineering can prevent sintering by raising the effective melting point. Phase-change nanoparticles for drug delivery rely on precise melting behavior. The paradox allows tuning release temperatures over a wide range. Selective melting of nanoparticles with different surface chemistries enables complex patterning in nanomanufacturing. Here's another helpful analogy. Think of atoms in a nanoparticle, like people in a community. Surface atoms are like people at the boundary of a community with fewer social connections. Core atoms are like people in the center with full social networks. A bare community with weak boundary connections is less stable and easier to dissolve. This is like melting point depression. But if you add strong infrastructure at the boundary, like community centers and connecting roads, the whole community becomes more stable. This is like ligand stabilization. Internal social tension is like strain. Moderate tension can strengthen bonds through shared challenges, while excessive tension weakens the community. Let's do another quantitative example, focusing on strain effects in palladium nanoparticles. The bulk melting point of palladium is 1828 Kelvin. The heat of fusion is 16.7 kilojoules per mole. The volume change on melting is about 3%. Assume a compressive stress of 2 gigapascals in a 5 nanometer particle. The melting point increase due to strain is delta Tm strain equals negative 1828 times 0.03 divided by 16,700 times 2 times 10 to the 9, which gives 66 Kelvin. So compressive strain alone can increase the melting point by 66 Kelvin. This is a significant effect. But the size effect for a 5 nanometer particle would decrease the melting point to about 1650 Kelvin. The net melting point is 1650 plus 66 equals 1716 Kelvin, so the strain partially compensates the size effect. Here's an interesting question. Can we engineer nanoparticles that reversibly switch between high and low melting points? The answer is yes, using stimuli-responsive ligands. For example, pH-responsive ligands can bind strongly at low pH and weakly at high pH. At low pH, strong ligand binding increases the melting point above bulk. At high pH, weak binding allows the normal size-driven depression to dominate. This creates a pH-switchable melting point, which has applications in smart materials and sensing. For very small nanoparticles below 2 nanometers, quantum mechanical effects also become important. The electronic structure transitions from continuous bands to discrete molecular-like levels. This is called quantum confinement. The energy levels are quantized according to En equals n squared, h squared divided by 8 meters L squared, where L is the particle size. Quantum confinement can preferentially stabilize the crystalline phase over the liquid, leading to additional melting point elevation. This effect is strongest for clusters below 2 nanometers, where quantum confinement is significant. How do scientists actually measure these melting points? Several techniques are used. Differential scanning calorimetry, or DSC, measures heat flow as temperature increases. A peak indicates melting. In situ transmission electron microscopy allows direct observation of melting in real time at the nanoscale. X-ray diffraction monitors the disappearance of Bragg peaks as the crystalline structure melts into liquid. Computer simulations using molecular dynamics can predict melting behavior and validate theoretical models. Let me summarize the key concepts we've covered in this lesson. Classical thermodynamics predicts that smaller particles should melt at lower temperatures due to surface energy effects described by the Gibbs-Thomson equation. However, the paradox is that some nanoparticles actually melt at higher temperatures than bulk due to ligands, strain, and shape effects. 3 key factors that can reverse the expected behavior are surface ligand stabilization, internal lattice strain, and particle shape and faceting. The net melting point change depends on the balance of all these contributions, which can be positive or negative. Understanding this phenomenon enables applications in nanosoldering, thermal stability of catalysts, and smart nanomaterials. We can engineer melting points over a wide range by controlling surface chemistry, particle morphology, and strain state. This paradox beautifully illustrates that nanoscale behavior cannot be simply extrapolated from bulk properties. Nanoscience reveals emergent phenomena that arise from the interplay of size, surface, quantum, and structural effects. A complete understanding requires combining classical thermodynamics with surface science, mechanics, and sometimes quantum mechanics. The field of nanothermodynamics continues to reveal surprises as we explore new material systems and measurement techniques.